Metal oxide semiconductor field effect transistor. Don't worry, that's the only time I'm going to say that. We normally call them MOSFETs. MOSFETs come in many shapes and sizes, known as packages, from the tiny little SOT23 to the ubiquitous TO220, right up to the chunky SOT227. MOSFETs can also be combined together, with thousands, millions, even sometimes billions, going into modern microcontrollers and CPUs. Another place where we can find multiple MOSFETs packaged together that I'm particularly keen on is power modules like this one. These are used in the beefiest power electronics, like inverters in electric cars. Something important to note is how so many of these larger packages are dictated almost entirely by their cooling requirements. That they all have a large exposed face to get the heat out using something like a heatsink. Where does this heat come from? Well, you'll know soon enough. I just want to give a really quick disclaimer that this video is going to be mostly focusing on the main use for MOSFETs, which is in a digital sense, using them as a switch. I think the majority of what I'm going to cover will still be quite useful to know if you're one of these strange analog people. Now, this is the part where most videos on YouTube will switch to some generic animation of electrons moving around to explain the rest. But I don't think that's a very good way of teaching. So what I've done is I've made some circuit boards to help illustrate things. A typical MOSFET will have 3 pins, the gate, the drain and the source, labelled here G, D and S. In the centre of the board I've put the symbol for a MOSFET, which is certainly on the more intricate side of component symbols. I've designed 5 other circuit boards based on this layout of increasing complexity, and we're going to start with this one. Some of you may recognise this MOSFET because it's not actually a MOSFET, it's a relay. But I think a relay is perfect for an initial explanation of how a MOSFET works. I have here 2 leads from my power supply, a positive and a negative. If I put the negative on the source connection of our MOSFET, and the positive on the gate connection of the MOSFET, then hopefully you'll be able to hear and see our MOSFET turning on when I apply 5 volts. So this shows that if we apply a positive voltage between our gate and our source, the MOSFET will turn on. And when we then remove this voltage, the MOSFET will turn back off. But what does it mean for a MOSFET to be on? Well, to show that we're going to need a load, so for that I have this lamp from a car. The lamp is wired so that we have positive from our 12 volt power supply, goes through the lamp, and is then on this crocodile clip. I'm going to connect this to the drain connection of our MOSFET. Then we have the negative terminal of that power supply, which is different to the power supply we're using on the gate, and I'm going to connect the negative to the source. This configuration is known as low side switching and is very common. Now if I put a voltage back between the gate and the source to turn the MOSFET on, you can see the lamp turns on. Amazing. Taking away the gate source voltage, again, turns the lamp back off. The part of the MOSFET that actually turns on and off is known as the channel, and the channel can actually conduct in either direction. So if I swap around my 2 connections to the lamp, current will now be flowing from the source to the drain. Everything still works. Now so far I've just been applying either 5 volts or 0 volts between the gate and the source. What happens if we apply a different voltage? Well, let's take a look. This multimeter is connected so that it's measuring the gate source voltage, and I'm going to slowly turn it up. As we can see, nothing happens until we reach what's called our threshold voltage. And that's the voltage you need to apply between the gate and the source to turn the MOSFET on. And now I'm going to stop at 5 volts because that's the maximum voltage that I can put on this particular MOSFET without causing damage. So let's go a bit slower this time, near the threshold. We're at 1.9 volts and our MOSFET hasn't turned on. I'm going to slowly turn it up. There we go. So on this particular MOSFET, the threshold voltage is 2.4 volts. Any more than that between the gate and the source, and our MOSFET is on. And here you can see the threshold voltage stated in the datasheet for my chosen MOSFET for this video. As you can see, threshold voltage is not a precise thing and varies quite a bit between MOSFETs, hence why a range of 2.5 to 3.5 volts has been specified for this device. Ah, isn't it beautiful? Ew, what is that? As you can see, our lovely clean MOSFET has grown a big ugly diode on its back. This is the body diode. Every MOSFET has one, and it's nothing to be ashamed of. You can actually see it in the MOSFET symbol. If you look here, there's the diode pointing between the source and the drain. So how does this body diode affect the MOSFET? Well, the main thing is that current can now flow from the source to the drain, so that's the reverse direction, even when the MOSFET's turned off. So you can see here I have nothing connected to the gate, so the MOSFET's definitely off. But if I take the other wire for the lamp and connect it to the drain, the lamp turns on. But I know what you're thinking, that didn't look very bright. That's because the body diode is not as good a conductor as the channel. So if I hook the lamp on permanently and then connect up the gate as well, you'll see that when I apply a voltage to the gate, the lamp gets brighter. And that's because with the MOSFET on, the current is all flowing through the channel, which is a much better conductor. So although the body diode means that current can flow all the time between the source and the drain, it's still important to turn the MOSFET on if you want current to flow in that direction, because it will be a lot more efficient. And here you can see the forward voltage of the diode in the datasheet. This varies a little bit with current, but essentially it's a fixed voltage drop that you're always going to have with current flowing through this body diode. And in almost every case, this is going to be greater than the voltage drop you'd have across the channel. So, is the body diode a problem? I'd say generally no, and in some circuits it's even useful to have. But there are definitely one or two situations where having it is annoying. Now sadly, real MOSFETs like this one aren't perfect switches for many reasons, and probably the biggest one is that the channel is actually a resistor. To demonstrate this, I've got my multimeter here measuring the resistance between the drain and the source. And what I'm going to do is I'm going to change the voltage I'm applying between the gate and the source. And what we'll see is that this essentially controls how on the MOSFET is. Right now I'm applying 2.4 volts, which as we saw from the datasheet is less than the threshold, which is somewhere between 2.5 and 3.5. That's why the multimeter is reading OL, which means over limit. So the resistance between the drain and source might be in the mega ohms, which we don't really care about. If I now turn up the gate source voltage a bit, we can see a resistance starts to appear. So now I've only taken it up to 2.5 volts, but we've now got 200 kilo ohms between the drain and the source. If I continue to increase the gate source voltage to just 2.6, we've now dropped to 10 kilo ohms. So you can see the resistance drops off very quickly. If I take it to 2.7 volts, we're now at 2 kilo ohms, and by the time I reach 3 volts, we're at 0. Now we're not actually at 0, I've fixed the range of my multimeter, so if I allow it to auto range, you can see we've still got some resistance there, about 90 ohms, and that's with a gate source voltage of 3 volts. Typically with a MOSFET like this, you'd be driving the gate at maybe 10 volts, and if I increase the gate source voltage that high, you can see we are now pretty much at 0 ohms. So what this shows us is that if we're using a MOSFET as a switch, it's very important that we keep the gate source voltage far away from the threshold voltage, either far above when we want the MOSFET on, or far below when we want the MOSFET off. Sitting around the threshold voltage will hold the MOSFET stuck between off and on, dissipating a lot of power and ultimately leading to its untimely demise. Now I know what you're thinking, you feel lied to. You were just told 5 minutes ago that the threshold voltage is the voltage that turns the MOSFET on, but now we know there's an entire spectrum of onness, and really the threshold voltage is just somewhere in that spectrum. Don't worry, you're not alone, and if we take a closer look at the datasheet, we can see the threshold voltage is actually specified for a particular drain current. So basically they're just saying, at this gate source voltage, this current will be able to flow. Now there is some physics stuff to do with electron density that determines this current, but really we don't care about that. We just care that the threshold voltage is still a good way to compare MOSFETs, even if it doesn't mean what we'd like it to mean. So if increasing the voltage between the gate and the source reduces this channel resistance, can't we just keep increasing it? Well, let's see what happens if I do. Right now I've taken it down to 3 volts. Let's have a look. This is at 7 volts, we've got 0.2 ohms. This is at 11 volts, 0.2 ohms. And finally, this is at 18 volts, still 0.2 ohms. Now, this is partly to do with the fact that we're below the minimum resistance that this multimeter can read. But it's also because MOSFETs have something called on resistance, which is a resistance that's always present no matter how hard you drive the gate. And there is a limit to the gate source voltage that you can see here in the datasheet, and it's very important that we don't exceed that, or really that we don't get close to it at all, because that will instantly destroy the MOSFET. So really, the channel of a MOSFET is a bit like a tap. I can control how much water is flowing through, but there's always going to be a limit, no matter how much I try to turn it on more. So what this means in practice is that you always have to think of a MOSFET like this, a permanent resistance on the drain that we can't get rid of. This resistance results in something called conduction losses, which is one of the two main sources of heat within a MOSFET. As you can see in this datasheet, this MOSFET has an on resistance of about 2 milliohms, which might sound like a tiny amount, but the losses caused by this resistance are proportional to the square of the current and dictated by the equation I squared R. So that means for this particular MOSFET, if we had 50 amps of drain current flowing through the channel, we'd have conduction losses of 5 watts, which may not sound like a lot considering there could be hundreds or even thousands of watts being controlled by this MOSFET, but it still needs to be dealt with, and how easily we can get this heat from the MOSFET's channel and out into the air is dictated by thermal resistance. You can see in this datasheet we have two thermal resistances. One tells us how easy it is for heat to get from the channel to the case, so that's this flat bit on the back, where we could then mount some kind of cooler. And the other is for if we don't put any kind of cooler on it, and that's the thermal resistance from the channel to the air. Note as well that in datasheets the channel is referred to the junction, because in other, usually older devices, instead of a channel there was something called a junction. One nice thing about the channel acting like a resistor is that it means it has a positive temperature coefficient, which is when the resistance increases as the temperature increases. This is really useful if we want to connect multiple MOSFETs in parallel, as it means they are inherently self-balancing. If one gets hotter than the rest, because there's more losses in it, its resistance will increase, so it will receive a smaller share of the current, which will then reduce its losses. Unfortunately, there's another problem with the channel, and that's something called saturation. This is where the channel can't handle any more current, and it stops acting like a resistor. This means the voltage drop across the channel increases dramatically, and therefore so do the losses. In power electronics circuits, saturation basically means your MOSFET's dead, unless you can turn it off very quickly, which is something that modern fancy gate driver chips are able to do, with a feature known as DSAT, which essentially monitors the drain source voltage when the MOSFET's turned on, and if it sees it suddenly going up when it shouldn't be, these gate drivers are actually fast enough that they can turn the MOSFET off and save it. It's very impressive. So let's take a quick look at saturation in action. What I've got here is one power supply connected between the gate and the source for our driving voltage, and another power supply connected between the drain and the source. And on that second power supply, we're measuring the current. So I'm going to start by applying 3 volts to the gate, and then I'm going to turn up the voltage across the drain and the source. You can see here we have a small amount of drain current flowing. We're currently in the ohmic region, which is where we want to be. The current flowing is equal to the voltage I'm applying divided by the on resistance for this specific gate source voltage. If I continue to increase the drain source voltage, we'll see that quite quickly the current stops increasing. So I'm at 1 volt, 3 volts, 6 volts, 10 volts, 15 volts, and right the way up to 30 volts, where you can see we still haven't really gone that far over 1 milliamp. So that's the saturation current for this gate source voltage, about 3 volts. And on this nice plot from the datasheet, you can see the saturation quite clearly, and you can see how it becomes less of a problem if we drive the gate with a higher voltage. Note how on the left-hand side, the voltage and the current are fairly proportional, and we have a nice straight diagonal line. But on the right-hand side, we can see where saturation has happened, and the current is almost flat, irrespective of the voltage between the drain and the source. Now, there are many analog applications that actually use this saturation region, and some very clever people in the past came up with some lovely equations to approximate this saturation current for any MOSFET and any gate source voltage. However, for power electronics, we do not want any saturation, so we won't be looking at this any further. Now, it seems like this channel resistance is only really a problem in between on and off states. So can't we just switch really fast and spend as little time as possible in this lossy, high resistance middle ground? Well, yes, of course. That's the whole point of a gate driver, is to drive the gate with a high current to turn it on and off as fast as possible. But wait a minute, what did I just say? Current? One of the key features of a MOSFET is that the gate requires zero current. While this may be true in steady state, so either off or on, transitioning between these states does actually require current. Why is that? Well, that's because between the gate and the source, there's actually a capacitance, so you have to imagine it like this. Here you can see a big capacitance between the gate and the source, and from now on we need to think of the gate as a capacitor that has to be charged to turn the MOSFET on and discharged to turn the MOSFET off. For example, if you just disconnect the gate circuit while the MOSFET's on, it will probably just stay on because this gate source capacitance holds the voltage that's keeping the channel open. Well, that's not a problem. You can charge and discharge a capacitor really quickly if you've got enough current. Once again, it's not that simple, sadly. You might have noticed this resistor. This is the gate resistance, and it's internal to the MOSFET, so there's nothing we can do about it. You can see it here on the datasheet. This resistance limits how fast we can charge this gate source capacitance, and in almost all switching circuits we will actually add more resistance externally, for reasons I'll get into later. So here we have, once again, the simple low-side switch circuit, with our lamp and our MOSFET, though this time it's the MOSFET with the gate capacitance. If I now turn on the gate supply, we'll notice two things. First off, there's a delay. The lamp hasn't turned on yet. And secondly, when it does start to turn on, it takes time to turn on, and the same is true for turning off. This is because our gate resistance limits the current we can put in and take out of this capacitor. And because we are switching off and on slower now, we are spending more time in this lossy region with the channel resistance soaking up quite a lot of power. This will cause the MOSFET to get hot, and is quite often a source of more loss than the conduction loss. If this loss isn't accounted for, with cooling on the MOSFET, it's going to ultimately result in release of the magic smoke. Now, you'll be able to find this capacitance on the datasheet. It's called input capacitance, or CISS, and while technically that also includes the gate drain capacitance, this is usually much smaller than the gate source capacitance, and will almost always be stated on its own as well, so you can subtract that from the input capacitance to get the gate source capacitance. Now you've probably been admiring these lovely PCBs I've been showing so far. These are from JLCPCB, the sponsor of today's video. I've been ordering PCBs from JLC for over a quarter of my life, and what I really love about them is how affordable and accessible they make this hobby. I don't think I would have made the leap into designing PCBs as young as I did if it wasn't for JLC's rock-bottom prices. Ordering from JLCPCB is as simple as drag and drop your Gerber files onto the website, select the options you want, and be taken aback at the incredible low price. They offer boards up to 20 layers, and some really nice options for high power boards like I often find myself buying, such as 2-ounce copper on inner and outer layers, edge plating, and copper filled vias. You can choose from 7 colour options for your silk screen, 6 of which I've shown you today. And if you're not sure about the design of the PCB, feel free to check out my KiCad video series, which walks through every step, including ordering on JLC. Now back to MOSFETs, and it's time to move on to the proper parasitics, starting with gate inductance. Now, spoiler alert, there is inductance on all 3 connections, but we're going to start by looking at the effect of the gate inductance, because that will explain why we need to add external gate resistance, despite the fact it increases switching loss. So, as we've seen in my previous video, now let's look at both together. What we get is a high voltage arc between the positive connector and the inductor, and this is thousands of volts, and is actually quite dangerous. Not only to people, but more importantly to circuitry. If the current passing through an inductor changes very quickly, the inductor itself will generate a large voltage in an attempt to keep the current the same. Even though these parasitic inductances on a MOSFET are typically in the order of nanohenry, the rate of change of current is so high that there can still be a significant voltage generated. Another similar problem is that when combined with the gate source capacitance, this inductance can form an LC tank, which causes oscillations in the gate voltage. These oscillations can cause the gate voltage to exceed the threshold after you've turned the MOSFET off, which will obviously turn the MOSFET back on, or at least partially back on, when you don't want it to, which is really bad. And the overshoots caused during turn on can actually exceed the maximum rating for the gate source voltage and permanently destroy the MOSFET. So because of these problems, we add the external gate resistance, which acts to dampen these oscillations and overshoots by absorbing some of that energy, and also reducing the rate of change of current through the inductor. The next inductance we're going to look at is the source inductance, the effects of which can be even worse than that of the gate inductance. And this is because in a 3-pin MOSFET, the source connection is used for both current through the channel from the drain and for driving the gate. Remember, it's the gate source voltage we need to change, not just the gate. So this means when we turn our MOSFET on or off, and the current through this inductance suddenly changes from, say, 50 amps to 0 amps, an even bigger voltage than in the gate inductance is going to be generated. And because the source inductance is still part of the gate drive circuit, or what's commonly referred to as the gate drive loop, the voltage generated by this inductance will actually appear on the gate, which can again turn on when you want it to be off, turn off when you want it to be on. It's not good. The best way to mitigate against this is to use a MOSFET with a Kelvin source connection. This is a fourth pin, which is essentially a second source, that you just use for driving the gate. This will almost entirely eliminate this issue, as long as the Kelvin source connection is actually made onto the silicon die and not just connected internally, which is what I'd call a fake Kelvin source. The second impact of the source inductance is on the drain source voltage. This is also affected by the drain inductance, so I'm going to add that in now too. Together, the source and drain inductance can once again result in ringing and overshoots, this time between the drain and the source rather than the gate and the source. And these overshoots are typically much bigger than those on the gate because the currents involved are much higher. In many applications, this inductance is more dependent on circuit layout and PCB design than the actual MOSFET itself, as these things can add sometimes significant further inductance. In the case of the humble half-bridge, which is 2 MOSFETs and a DC capacitor, this inductance is referred to as the loop inductance, and it includes the source and drain inductance of both MOSFETs, as well as the inductance of the capacitor and of the circuit between them. This is something that's really important to minimise in a half-bridge, if you want to switch fast and minimise your losses. And this is where modern surface mount components really come into their own. What I'll do here is I'm going to arrange these MOSFETs and this capacitor in a way that would be fairly typical for a half-bridge. The 2 of these MOSFETs would be mounted on a heatsink, and this capacitor would be on a PCB next to them. We can approximate the loop inductance by looking at the loop area. So that's the area marked out by the path of current from the capacitor through both MOSFETs and back to the capacitor. So you can see it looks fairly small in this case, but wait until you see a surface mount equivalent. This MOSFET is a 7-pin TO263 package. The silicon inside is pretty much the same as these MOSFETs, but the package is clearly much smaller, and even more so once you put it next to its friend. This is quite a modern package, and it's what a lot of the best current MOSFETs, especially silicon carbide, come in. If we combine that with a fancy modern capacitor, this is called a Ceralink, then you can see how much smaller the loop inductance is on something using modern surface mount components than old-fashioned through-hole. So even though it may make cooling more challenging, you might find there's a lot less cooling to do, because the parasitics are so low that we can switch a lot faster and have less switching loss. Interestingly, we can actually control the overshoot generated by the drain and source inductances, again using the gate resistance. This is because by increasing the gate resistance, we slow down how fast our MOSFET is switching, which reduces the rate of change of current. We're switching the same current, but in a longer time. And as our equation for inductor voltage shows, if we can increase that time that we're spending changing current, the voltage we generate will be lower. So in a lot of circuits, especially if you have a well-designed gate drive, the gate resistance is actually used to tune this overshoot. It's not to do with protecting the gate. Cool people even have 2 separate gate resistors, one for turning on and one for turning off. This is because it's often the case that one can be faster than the other for the same level of overshoot. And that's because the mechanisms that cause the overshoots during turn on and turn off are slightly different. That's it for inductance, we've covered all 3. Now time to return to capacitance. And next up is the drain source capacitance. This capacitance is charged up every time the MOSFET is turned off, and there's a voltage across it between the drain and the source. For example, in the half-bridge configuration of, say, an electric car inverter, I might have 400 volts across the MOSFET when it's turned off. That 400 volts has charged up our drain source capacitance. Now when we turn our MOSFET back on, there's only one place that the energy stored in this capacitance can go, and that's into the MOSFET. So this is obviously a bit of loss, and there's not really anything we can do about it. The faster we switch, the worse it'll be, because the more often this capacitance will be charged up and then discharged into the MOSFET. And this loss is commonly referred to as COS loss. COS, or COSS, is the output capacitance. And technically the output capacitance is actually the drain source capacitance plus the drain gate capacitance. But as with the input capacitance, the capacitance between the drain and the gate is very small, so almost all of the COS loss comes from the drain source capacitance. This COS loss is annoying because it's always there, even at low or zero output current, and output capacitance is bigger on beefier MOSFETs. So this means if you make a really chunky inverter in an electric car, your cost loss might be costing you 1 or 2% efficiency when you're just cruising along at a low speed. Now the drain source capacitance is also a bit weird. Its capacitance varies a lot with the voltage across it, and it drops off significantly at high drain source voltages. This means calculating the amount of energy stored in it's a little bit tricky. You can't just measure the capacitance with a multimeter and use the standard half CV squared. Because of this, the total charge stored at a given drain source voltage is often provided in the datasheet to make things a little bit easier. We're almost there, ladies and gentlemen. The final parasitic is the gate-drain capacitance, also known as the reverse transfer capacitance. Despite being the smallest capacitance, this is the deadliest in fast switching applications. And that's because capacitors like to try and keep the voltage across themselves constant, and the gate-drain capacitance is no different. When the MOSFET turns off, the drain voltage will rapidly rise. In our example from earlier of the electric car, this drain voltage is going to rise up by 400 volts relative to the source. And generally, the gate and the source, they stay together. The drain is the pin that likes to wander off to lands of high potential. Because of the capacitance's desire to keep the voltage across it the same, when the drain voltage shoots up, this capacitance tries to bring the gate with it. And I'm sure you're already shaking in fear at what this could cause. The gate being pulled up to 400 volts is going to destroy the MOSFET instantly. Well, this is an effect known as Miller turn-on, and because of that name, this is also often referred to as the Miller capacitance. The effect of Miller turn-on has become a much bigger deal recently, with the advent of silicon carbide MOSFETs, which are both higher voltage and faster switching than conventional MOSFETs. So looking at our capacitor current equation, we've got a bigger change in voltage in a smaller time. So that means the current through this capacitor that's going to be trying to charge up the gate is much higher. Luckily, we are mostly saved from this by our old enemy, the gate source capacitance. That's because this capacitance is much, much bigger than the gate-drain capacitance. So together they form a capacitive divider, and most of that current that flows from the drain to the gate through the Miller capacitance is just soaked up by the gate source capacitance. Miller turn-on is still a bit of a problem, and there's a few ways we can deal with this. Firstly is by using the lowest value of gate resistor possible, because the stronger we hold the gate down, the harder it is for the Miller capacitance to pull it up. We can also drive the gate negative, so instead of 0 volts between the gate and the source to turn our MOSFET off, we can actually apply a negative voltage, say -5 volts. And that means that even if the gate gets pulled up by a few volts, it won't turn the MOSFET on. And that's another thing that's very common in silicon carbide applications. There's also something called an active Miller clamp that's another fancy gate driver feature, a bit like DSAT. And that's essentially like a second gate driver with no gate resistance. So it's really strong for pulling the gate down and keeping it down. This second gate driver only kicks in once the gate has been pulled below a certain voltage. So that means it doesn't result in the ringing that you'd expect using no gate resistor. And here in the datasheet we can see CRSS, which is the reverse transfer capacitance, or the Miller capacitance, or the gate-drain capacitance. And as with the drain-source capacitance, this Miller capacitance is very dependent on voltage, as we can see in this plot. So once again, this makes calculations and simulation non-trivial. So that's it for our parasitics. Who would have thought that a simple electronic switch could get so complicated in just 30 minutes? I'm now going to really quickly run through a few strategies that you should keep in mind to try and reduce the effect of these parasitics. There's something called soft switching, which is basically where you turn the MOSFET on and off, either when there's 0 voltage across it or 0 current flowing through it. This effectively means you have 0 switching loss, and the effects of a lot of the parasitics simply don't exist. It's a very cool thing, but unfortunately it's quite complicated to control and very difficult to implement in some topologies. Next, as I showed before, especially for a half bridge, loop area should be kept as small as possible. This applies not only to the power loop, but also to the gate drive loop. And an easy way to keep these areas small is to put opposing current paths on different layers of the PCB. So for example, for the gate drive, you might have your trace connecting the gate to the gate driver on the top layer. So then all you need to do is run the source trace back to the gate driver in parallel on the layer below. And you can see now the area between these two is very small, which means the inductance is very small. This works particularly well on a PCB with more than 2 layers, because the layers will typically come in pairs that are very close together, as you can see here on the stack-up diagram for a 4-layer PCB from JLCPCB. Another thing that's really important is, even if you're using a device without a Kelvin source, try and keep the gate loop and the power loop as separate as possible because of the effects I've mentioned to do with inductance that's in both paths. If you're making something like a half bridge and you need a big capacitance, let's say you're using these surface mount devices but you have to have as much capacitance as this film capacitor contains, then what you should do is you should add local decoupling, so that's a smaller capacitor like this Ceralink, as close to the MOSFETs or half bridge as possible. Then this capacitance will deal with the highest frequency current, and the bigger capacitance that you can't put as close will deal with the lower frequency components. If you've tried your best but there's really nothing else you can do to stop the overshoots and the ringing, you can add some snubber circuits that will soak up some of the energy of the overshoots and the ringing, but these will bring additional board or layout complexity and losses. Now, to protect myself from rage and fury in the comment section, there's a few things I have to mention. First off is that everything I've shown is for N-channel enhancement mode MOSFETs. So let's go through those things one at a time. First off, what is N-channel? Well, MOSFETs come in two flavours, N-channel and P-channel. And basically, P-channel is just the opposite to N-channel. Current flows in the opposite direction, you drive the gate with a negative voltage instead of a positive voltage, and they're also a lot less common. And that's because P-channel MOSFETs are objectively worse. For the same amount of silicon, we can't get as much current through a P-channel MOSFET, which basically means a MOSFET of the same size and cost will be 2 to 3 times worse if it's P-channel. And that's the reason that in power electronics, we almost exclusively use N-channel MOSFETs. There are a lot of applications that don't really care about these downsides for P-channel, the biggest one being CMOS, which stands for complementary metal oxide semiconductor. And the complementary refers to N-channel and P-channel. So CMOS, which is what's used inside microprocessors, logic gates, basically anything that's digital and not high power, that uses both N-channel and P-channel in beautiful harmony. Then the second thing I mentioned is enhancement mode. What's that? Well, again, there's a second weird type of MOSFET called a depletion mode MOSFET. These are again sort of the opposite to enhancement mode. A depletion mode MOSFET conducts when there's no voltage between the gate and the source, and we apply a negative gate source voltage to turn it off. So it's essentially just a normal enhancement mode MOSFET, but with an offset voltage applied to the gate. That means it's on by default. Again, these aren't as good for power electronics, and they're also a bit weird, so they don't see a lot of use. But one common application is internally within current and voltage regulators. And actually, finally, to finish off, we're going to take a look at two devices that are very similar to MOSFETs, but technically aren't MOSFETs. The first is the IGBT, which stands for Insulated Gate Bipolar Transistor. Now the gate part, that is almost exactly the same as a MOSFET. We can drive it in the same way, we even drive it with the same chips. But the difference is on what the gate is doing. In an IGBT, the drain and the source are replaced by the collector and the emitter, and the channel is replaced with a junction. IGBTs are more similar to silicon carbide MOSFETs than standard silicon MOSFETs, at least in terms of the voltage they can operate. And IGBTs are very common in anything high voltage, really. Most electric cars are still on IGBT, with a few moving to silicon carbide MOSFETs in recent years. Electric trains use very beefy IGBT power modules, and really, despite advancements in silicon carbide MOSFETs, the low cost of IGBTs, combined with their high voltage and current capabilities, mean they remain the king of high power applications. Now this second device is probably going to be a little bit tricky to see. We're comparing it to the SOT23 MOSFET, and it is a Gallium Nitride transistor. There are a lot of people that refer to these as MOSFETs, but technically they're not MOSFETs. They have several names, the most common of which is HEMT, H-E-M-T. HEMT stands for High Electron Mobility Transistor, and electron mobility is a bit of a physics thing that we won't go into. But basically, gallium nitride is cool. This little MOSFET is the humble 2N7000. It's rated to block a maximum of 60 volts when it's off, and it's rated to conduct a current of up to 200 milliamps when it's on. For comparison, this gallium nitride device from Nexperia is able to block 100 volts when it's off and conduct 60 amps when it's on. That's right, 300 times the current of the old silicon MOSFET. Something that's really cool to see on the gallium nitride devices is the way they package them. So you can see, hopefully, with the reflection on the light, this is actually a silicon die. And they've just put some solder on the bottom, a bit like a BGA package. Now, I'll include a picture so you can see the bottom of it better. but those stripes of solder actually interleave drain source, drain source, drain source, and that's to keep the parasitic inductance as low as possible. And that's something that's really cool with the advent of gallium nitride especially, is that packages have had to change dramatically to bring down the parasitics. Otherwise you wouldn't be able to get the benefit that the actual semiconductor can provide. The two little solder pads at the top are the gate and the Kelvin source, which I mentioned earlier. Right, well that's it. Well done for making it to the end. Hopefully everybody's learnt something new, and hopefully you've enjoyed the video. This one's been in the works for over a month, so make sure if you enjoyed it to put a thumbs up and subscribe for more. Thank you very much for watching, and goodbye.